Okay, welcome back. And so now, before we jump into the next definition, I want to take a moment and talk to you about the last example that we did. And I encourage you to go back to that example and calculate the same approximations for the right endpoint approximations for n equals 4, 8, and 32. Okay? You'll notice that for the right endpoint approximations, you tend to overestimate the area on the curve because you'll see that all of the values are over 8. And as we saw in the last example, the left end point approximations were all under 8, but they were all both going towards 8. And so we give this idea, this intuitive, we form a conjecture that, hey, it seems like this is heading towards 8, that the area under the curve from 0 to 2 for this function is equal to 8. Okay, now, we're going to build off of that. Now, because if we use the left endpoint approximation and the right endpoint approximation, we tend to either underestimate the value of the area under the curve or overestimate the value of the curve. And we also see that as we increase the number of rectangles that we're summing up, that our approximation gets better and better and better. And so we're going to introduce this idea of a Riemann sum. A Riemann sum was actually developed by a famous 19th century mathematician, Riemann, who developed this notation. Okay, so let's start with the definition of what a Riemann sum is. Okay, so now, it says let f be a function defined on a closed interval a to b, and let p be a regular partition of a to b, of the interval ab. Let delta x be the width of each subinterval from x sub I minus 1 to x sub I. And for each I, let x star sub I, or x sub I star, be any point we wish to choose in the interval x sub I minus 1, comma, x sub I. So basically we're just going to say, we're going to just take a sample point, any sample point. We're just going to, it could be a random sample point. Okay? We're going to define a Riemann sum a Riemann sum is defined as follows. It's the summation from I equals 1 to n of the function defined at x sub I star times delta x. So it's not anything really much different than what we were doing with the right endpoint approximation, the left endpoint approximation. We could also introduce midpoint approximations. So all we're doing is it doesn't really matter, right? So the idea is it doesn't matter where we pick our point. Because what we're going to do is we're going to say, hey, we're going to let n get larger and larger and larger. So what's happening? These subintervals are getting smaller and smaller and smaller. Well, they're going to get smaller and smaller and smaller until we're at a single point, right? So if we choose a sample point within a subinterval, and as we start to decrease the size of the subinterval, the width of the subinterval by increasing n, well, what's going to happen? It's going to start going to a single point, and of course, whatever that point turns out to be, it doesn't matter, right? So eventually it'll just be x, okay? For all real numbers, since we're dealing with functions, right? So that's where we're heading. So anyway, that's the definition of a Riemann sum. And again, as n gets larger, this also becomes a better and better approximation, okay? But this is going to be the foundation of what we're going to use to define the area under the curve. Okay, have a great day.